Okay, hello everybody. This is the higher level content B31 for gas exchange. However, we're going to start that topic with something slightly different. It will be from chapter 2 B23. Remember, there was some few higher level stuff there that we're going to bring to when it's relevant. And we're going to start that now. And the first thing is that remember that cells were kind of couldn't be too big without restricting their surface to volume ratios and the ability to get nutrients and exchange with materials with the outside surface with the whole of their cells if they got too big. Well, there are ways for cells to kind of get around that, or even just increase the surface to volume ratio, even if they're the same size. And that will come into play here for the gas exchange. I thought it would be good to include here. So cells that are specialized for these will have adaptations to increase the surface area, and being long, flat, will increase the surface area ratio. Great spelling here, Peter, whatever. But being flat and long is called squamous, if you want to use fancy words. Having projections on the surface, like things, part of the cells protruding outwards, also does this. So you see here, red blood cells, those are flattened, so squamous. And here you see some microvilli, so protrusions on the surfaces of cells that are in the convoluted tubule cells of the kidney. We'll get back to talk about those later when we get to the kidneys, but the syllabus liked them, so let's bring them up now. But let's continue. The parts of B23 that's really relevant for B31 gas exchange is this one, the adaptation of type 1 and type 2 pneumocytes. So if we look at the alveoli in microscopes and we take a micrograph of them, you will see them like that. So this is the alveoli here, all these little air spaces in here, those are alveoli, and they see that here's the single line or single layer of cells that make up their borders. There's two types of cells in those borders, and one type has to increase the surface area, so that's why I thought I'd bring up that previous slide as well. And those are the type 1 pneumocytes. Those are make up the most of the surface here. They are very thin cells, you can see them here. Stretched out, thin, squamous, basically. So they are, I think they're about 50% of all cells in the alveoli, but they cover 90% of the surface. And these type 1 pneumocytes, those are the ones involved in creating this gas exchange surface of the alveoli. But then we have the other ones there, though you'll see them here in the micrograph, and here's a model of them. Those are the type 2 pneumocytes. They are the ones that release that surfactant on the in the alveoli. So they have a very different look to them, and inside them they will have many small secretory vesicles called lamellar bodies, if you wish, and they then contain this surfactant and release them at the surface there, so you get this surfactant covering the inside of the alveoli. So this lung alveolar tissue is basically a type of tissue that consists of many different cell types to be able to do the type of functions that they have to do to provide the different adaptations that they have. So this one became relevant to me to explain or relevant for this chapter, so we brought those two examples in from B23. But here we go for the actual B31 higher level. And the first one is to talk about oxygen dissociation curves from hemoglobin. And we're just going to first talk about the unit here, which is called kilopascal. So we sometimes quantify the amount of a specific gas in a mixture by their partial pressure. So in any mixture of gases like air, you get a total pressure of the mixture, and each gas contributes to that pressure. And the contribution of a single specific gas to that total pressure is called the partial pressure. So it's basically if you take the full pressure of the mixture and you take the relative the percentage of molecules of that gas in the mixture, I think you get the partial pressure that way. And that's the SI units of kilopascal. So that's why what this actually means, this partial pressure. So it's the contribution of a given gas to the full pressure inside a tissue, for example. And this is what we call the oxygen dissociation curve of hemoglobin. So you can see basically during which partial pressures of oxygen hemoglobin is either fully saturated with oxygen or no saturation, and has this S-shaped curve. And that's maybe a little bit weird. Maybe one would ideally think that the shape here would be linear, so that as the amount of oxygen in the environment increases, the hemoglobin starts to fill up linearly, but it does have instead this S shape. So we're going to try to explain how that works. So this is a hemoglobin molecule right here, has these 4 subunits called the alpha and beta subunits, so 2 alpha, 2 beta. And in each of these 4 subunits, you can bind 1 oxygen gas molecule, and each oxygen gas molecule has, of course, 2 oxygen atoms. So a single hemoglobin can bind 8 oxygen atoms. And let's see. So the kind of binding of oxygen to hemoglobin has this, or there's this feature called the cooperative binding that helps oxygen to bind to hemoglobin. So this means that when one oxygen molecule binds, it changes the conformation of the molecule. So now it becomes easier for the next hemoglobin to bind, and that changes the conformation further, so it makes it even easier for the third oxygen gas molecule to bind, and that changes the conformation even further. So the 4th one has really easy time binding. So that's going to help us explain this curve. There's one thing we're going to bring up here as well, is that CO2 can also bind to a different site on hemoglobin and change how it works. It doesn't help us explain the S curve here, but it is an important part of hemoglobin, and it's going to come into play later. But when CO2 binds to hemoglobin, that makes hemoglobin less sensitive to, or less likely to pick up oxygen. It's called affinity, how easy it is for something to bind. So that means that oxygen will unload from hemoglobin when CO2 levels are high. But we'll get back to that later. So looking at this S curve again. So as the O2 levels are kind of high, as in the lungs, due to cooperative binding, you will basically have super loaded hemoglobin. So all the hemoglobin will be fully saturated if everything works normally. However, when you start getting into moderate partial pressure, or environments with moderate oxygen levels, partial pressures of oxygen, small changes can lead to rapid changes in how saturated hemoglobin is, basically how much it loads O2 or how much it unloads it. And in low oxygen environments, such as respiring tissues, hemoglobin will be releasing a lot of this hemoglobin. But basically this curve looks like this, as basically when there's low oxygen levels, you'll have very little saturation of hemoglobin. But as these increase, you basically start seeing this increasing steepness of the curve, and that's because of this cooperative binding. Otherwise it would be linear. So that generates this steep part. where you will have big changes in CO2 or in O2 levels. And that makes the whole curve look like this. So this is basically how it looks at the lungs. You have full binding of hemoglobin, and if you become hypoxic for some reason, for example during stress or super high exercise, you will not have O2 bind to hemoglobin, which would suck because you need that O2 in your cells to do cellular respiration. Now, when you are a fetus, fetuses, you will have a different hemoglobin. So fetuses, of course, they can only get oxygen from the maternal bloods. Their own lungs aren't breathing anything, right, other than pee water. No, the water in the placenta has a little bit of pee in it from the kid, so they will get that into maybe not the lungs, actually, probably close it with epiglottis, but whatever. So they have to at least get the O2 from the mother's blood. And so when you're a fetus, you have a different type of hemoglobin. So normally you have these alpha and beta chains on the hemoglobin, but when you're a fetus, you instead produce alpha and gamma chains in your hemoglobin. And these gamma chains instead make hemoglobin that has a higher affinity for oxygen than adult hemoglobin. This means that oxygen is more likely to bind to the fetal hemoglobin. So when we look at the oxygen dissociation curves for these, you'll see that the fetal hemoglobin is basically shifted to the left, which means that it's more likely that at a given partial pressure of oxygen, it will be going to the fetal hemoglobin instead. So basically in the placenta, I would assume that the partial pressure of oxygen would be somewhere here in the middle range. So basically your adult hemoglobin will be sometimes losing oxygen molecules, and those will then be more likely to end up on the fetal hemoglobin than they would on the adult hemoglobin, because the fetal hemoglobin has higher affinity for the oxygen. So basically this allows the fetus to basically steal oxygen from the blood and hemoglobin of the mamas. Neat. Otherwise they would die. And the final part of B31 that we're going to bring up is called the Bohr shift, and it's something that we need to be able to explain. So basically, the Bohr shift means that it's a phenomenon where this magenta line here shows the normal saturation, dissociation curve for oxygen with hemoglobin. But when CO2 levels increase, that's when we see the Bohr shift, and that's when the curve shifts to the right. So it becomes lower affinity for oxygen. And that's because of two things happening when CO2 levels increase. First, we have this allosteric binding of CO2 to hemoglobin that we talked about before. So basically, hemoglobin can bind both CO2 and O2. And when CO2 levels are really high, there's a bigger chance of CO2 binding to the specific hemoglobin molecule. And that will cause then basically your O2 to drop off of hemoglobin and become available for your cells. And that's neat. And that's only, however, a small portion of all the CO2 in your tissues. Most of CO2, when they leave your tissues and enter the blood, they will go into the red blood cells. And inside the red blood cells, there's of course water. So the CO2, I forgot to say that it's because the pH is lower, but that's because these CO2 molecules then go into the red blood cells, and some of them will combine with water and form carbonic acid. Sorry for not doing lowercase numbers on these ones. I hope you can forgive me. I didn't remember to do that. Anyways, some of these carbonic acid molecules will dissociate to form the bicarbonate ions and protons to reduce the pH level. And some of these protons will bind to hemoglobin and continue to reduce affinity for O2. And that's basically the main two reasons why the Bohr shift happens. So the Bohr shift is something that happens to your blood when it gets to the respiring tissues where there's a lot of CO2, and helps then unload the oxygen further, so your cells can do aerobic respiration. And that's really neat, isn't it? Cool. So that was the higher level stuff for B3.1, and with the companion parts of B2.3. Enjoy.